Hey there, guys. I'm just playing with my physics toys. Don't mind me. In any case, um, uh, I think I have a video to record. Right. Okay. Let's do that video. So we're supposed to explain this static equilibrium problem right here with the ladder leaning up against the wall. All right. In class, we already drew the force diagram, so that's already on there. For part B, though, we're supposed to figure out, I changed the text slightly from class, but we're supposed to find what is this normal force and what is this friction force. Now remember, this is static friction, so it's actually not necessarily going to be friction is fun, because it's not necessarily at that maximum angle, or I guess minimum angle in this case, before it's going to start to slide. Okay. The other approximation that we made to make the question a little bit easier to work out is suppose the top end has frictionless rollers on it. Okay, so I'm actually going to go ahead and erase that friction force since it says it's not there. All right. If I want to find out what that normal force is and what that friction force is, I'm going to start by doing what we did in class, which is for any static equilibrium question, you write the sum of the forces and the sum of the torques. Now, where this one's a little bit different from the other questions we've done is it's leaning against the wall at an angle. And some of those forces are therefore not like straight up and down or something like that. Some of them are sideways or sideways, I guess. So we have both x and y to look at. All right, well, let's do that then. The sum of the forces in the x direction first. Looks like we have N2 to the left, and we have F1 to the right, and that's it. And assuming that the ladder isn't slipping, some of those forces would be 0, which means that we could actually say then that F1 is going to equal N2. Right, that's not really an answer, okay? All the answers here really are going to need to end up being something in terms of the weight of the ladder and the angle. So N2, we're going to ultimately discover, is something in terms of mg and theta, but for right now, that's a good starting point, right? The friction force does have to equal whatever that normal force is. All right, let's do the y direction. Well, vertically, actually, we only also have 2 forces, since I erased that other friction force, which is why I said it would be more complicated with that other friction in there. All right, so that means that we can say N1 equals mg. That's actually an answer. We're done. We got one, right? The normal force on the floor being the weight of the ladder actually shouldn't surprise you all that much. I mean, if the floor is holding it up, the weight it has to be holding up is the normal force. Okay. Now, if there were friction here, then it wouldn't necessarily be like that, which again is why we erase it to make it a simpler question. We could work it out, it just would be more time consuming than I can probably feasibly cover in this video. All right, now if I want to find out what the friction force is, this is actually where torque has to come into it. Remember, for torque, you can, for the torque equations in your static equilibrium, you can write it about either pivot point. So there are 2 pivot points here that make sense, right? One would be if you imagine like this wall suddenly disappeared, then the ladder would fall that way, and that would be a pivot point. All right. The other pivot point that you could imagine would be if the floor disappeared and started sliding or started falling that way. I agree that's a ridiculous scenario. The floor's not actually going to disappear, but those are your 2 reasonable pivot points. Okay, so the ends of the ladder are your pivot points. All right. So I'm going to do the torque around. It doesn't actually matter which end we do. However, some pivot points make more sense than others, okay? And usually the pivot point that you want to pick is the one that's going to make the most forces disappear from your work. In other words, the bottom end. If I use the bottom end, neither of these two forces end up exerting any kind of a torque, because guess what? They're acting at the pivot point. So if the bottom is my pivot, then I don't have to worry about N1 or F in my torque equation. It's just going to be mg and N2. All right. Now, it's not just going to be mg times the radius and then minus N2 times the radius. It's not. And the reason it won't just be that is because torque's a cross product. For my weight of my ladder, if I'm using the bottom here as my pivot, that right there is my radial vector. Okay, so that's where my L over 2 came from, right? The weight acts at a distance of L over 2 from the end of the rod, or the end of the ladder, whatever it is. But this angle between these isn't 90. It's something else. All right, what is it anyway? Well, there's the angle that we talked about in the question. So that means this angle is the complementary angle to it. All right. Torque's a cross product. That means that F cross R is FR sine of the angle between the force and the radius. All right. Fine. So the angle I'm going to be using here really in this equation is this one. If I was going to use sine of theta, theta isn't the one I drew down here. For this equation, it's the angle between the force and the radial vector, which is the angle up here at the top of the triangle. All right? Well, instead of writing in like sine of 90 minus theta, there's this trig identity that you ought to remember, which is that sine of 90 minus theta is cosine of theta. If you aren't sure about that, you can try out cosine 30 and sine 60, and you discover that they are the same because 30 and 60 are complementary angles. This works with any two complementary angles you want to look at. All right. So that means the torque produced by my gravity then isn't just mgl over 2, it's mgl over 2 cosine theta. All right, same kind of story for the torque produced by that normal force up there. It's acting at an angle as well. And you could do some geometry here and figure out that this angle is the given angle. All right, so this time the radial vector and the force vector are acting apart by the angle that you were given. So it'll be sine theta right there. All right, so again, to recap on my choice of cosine and sine, it's all based on which angle actually represents the angle between the force and the radial vector. In this case, it was the complementary angle. This is there. It's the complementary angle. No, hold on. There. It's the complementary angle from the top of the triangle, right? For the other one, it's actually the angle that I was given, so therefore F R sine of this angle. All right. Now, where do we go from here? Well, where we go from here is I was trying to find F1. And what we got way up here was F1 is N2. So I need to know N2 if I want to actually figure out what F1 is. Oh my goodness, this equation allows me to solve for that. This is a good day. Okay, so N2 L sine theta equals mg L over 2 cosine theta Factor val cancels, and we'll get N2 equals mg over 2 cosine over sine. So that'll be cotan theta. Let me write that a little more neatly, because that looks kind of good. That's a word. Trust me. All right, mg cotan theta over 2 is my normal force, and therefore also my friction force. All right. I like it. That'll work for me. All right, now the last part of the question where it says, what's the minimum angle before the ladder slips? Well, all right. The angle at which, the friction force at the moment that it's just barely going to slip is going to be given by friction is fun. The normal force in this equation, if you're at that maximum angle, is this N1 right here. And N1 we found out up here is mg. That won't change with the angle as long as there continues to be no friction up here where it's speaking of. All right. And then we can set that equal to our friction force that we got from the previous question. All right, so, I'm sorry, I didn't actually, there's a number you needed here. Let's say mu equals, I'd have to say something like mu is 0.5. There you go. All right, so the angle at which it's going to slip, cancel, cancel. Mu is 0.5 equals cotan theta over 2. We'll get all right, and you do a little bit of trig, and what you're going to end up with is exactly a 45-degree angle. All right, I didn't even have to get a calculator for that. That's remarkable. All right, so there we are. Hopefully that's the last type of question you need to look at before you're going to be able to do homework 3. So there you have it. You're able to do homework 3 now. All right, I hope that was helpful. If not, leave complaints in the comments. No, don't do that. Don't do that. You'll bring down my rating on YouTube, which I actually don't care about at all. Okay, hopefully that was helpful. So have a good day. I'll see you in class.